the first kind of sampling distribution that we'll explore has to do with sample proportions. To refresh your memory, when we talk about sample proportions, we usually mean from a sample of size n, lowercase n, x of those are of interest to us. So maybe we're separating this sample into two subsamples, right? For instance, if we are talking about a sample of CO2 levels, collected at Mauna Kea Observatory, then this sample, right, consists of quantitative data, continuous quantitative data, and it ranges from about 360 parts per million to about 450 parts per million. So these data values can range anywhere in here. And let's say our event of interest is the ones that are higher than 408 parts per million. So all the ones that are above a certain threshold. Okay. So then our sample proportion which we denote by p hat, that little caret is a hat, is the number of those data values in the sample as a proportion out of the total sample size. So to illustrate that, and to think about this as a random variable, then this event of interest that we're curious about, that we want to know more about the sample proportion, right? Every random outcome falls into one of these two events. Either it's greater than 408 or it's not, at or above. So let's suppose we take a random sample of 30 observations. And so there's x1, x2, all the way through x30, and our sample proportion from this specific random sample is the number of data values at or above, above 408 parts per million. And that we take that out of our sample size. So for instance, if there's 22 out of the 30 observations have CO2 levels that are above 408, then it might be 22 out of 30, and then we can write that as a decimal number if we're so interested in doing so. That's 0.73. So this is a single value for the sample proportion random variable. The sample proportion random variable, which we denote by capital P hat, is a random variable that takes on the values of sample proportions from random samples from this distribution. So in other words, if we could collect all the possible, so we have random samples of size n, and from each of those, right, we get these specific sample proportions. And each of those is a real number between 0 and 1. And the question then is, what does this distribution look like, right? So we know that it takes on values between 0 and 1, but what else can we say about this random variable? What's its probability distribution? So to understand that, we have to think about how to make inferences from these distributions. So if we said that each random sample contributes a sample proportion, right? We can think about this from the frequentist approach of in the long run, right? So as the number of samples increases, we will get a histogram or a relative frequency distribution that approximates the distribution of p hat, this random variable. And if we simulate this, we'll actually see that sample proportions are very special in that they have some specific properties, right? So one of these things that we'll see, and this is a theorem actually, where we'll have to use a little bit of imprecise language because we'll see clearly why it is what it is in a later section. But if we are taking samples of sufficiently large sample size, and that's where I'm saying that this is somewhat imprecise because sufficiently large is not, we're not defining that here, but we will. And we know the population proportion, so the parameter that corresponds to the sample proportion, which is population proportion, is P, then P hat is approximately normal with a mean that is equal to the population proportion. So in other words, in the long run, the expected value of this proportion random variable is the population proportion. And the standard deviation of this random variable is the square root of p times 1 minus p divided by n. So it depends not only on the population proportion, but also the sample size. But super importantly, it's normal. We can use what we've discussed in the previous sections about working with normal distributions to talk about sample proportions. So, for example, let's just get some practice in with this. So, in a previous example, we've established that the population proportion, P, of transfer students at a UC campus, a University of California campus, is 0.30. So that represents the total number of transfers out of the total number of UC students. So that's the population proportion. And we suppose that in an observational study, we selected 50 students at random, which we'll find is sufficient for our purposes of finding a sufficiently large sample size, and 14 are transfer students. So I have a few questions for us here first. So 1, what is the sample proportion from this specific sample? We should be able to find that by a simple computation. 2, what is the distribution of p hat, the random variable of the sample proportions? And 3, what's the probability of finding a sample proportion that is less than or equal to than the one in this study? Another way that this might be phrased is as extreme as the one in this study. So when we say extreme, we mean further away from the mean. And, in other words, we define this value as starting a tail either on the high end or on the low end of the distribution. So 1, what is the specific sample proportion we're looking at? Well, we take our number of data values in this sample that are of interest to us out of the total sample size. So that's 14 out of 50. And we find that that is actually equal to 0.467. So that's actually higher than our mean. So what we're looking for then is, so we'll get to that in a second. But first, then what is the distribution of p hat? So the sample size 50 is large enough for us to say that p hat is normal with mean p, which is 0.30, and the standard deviation which is the square root of p1 minus p over n. And we find that that is 0.065. So we now have all the parameters for this normal distribution, and we can use this to find probabilities, right? So 3, we're asking for what's the probability that we find a sample proportion that's less than or equal to this value that we found, 0.467. A few ways of doing this. So 1, we know that this is a normal distribution, so we can use normal CDF. We can also standardize. Okay, so if we choose to standardize, we may write that the specific z-score for this value, 0.467, is going to be the value that we found minus the mean of the distribution divided by the standard deviation of the distribution. So we have 0.467 minus the mean being 0.30 divided by 0.065. One thing to note here is that we're working with specific values here, but another way of writing this is we can get the standard normal distribution back by writing z is equivalent to p hat minus the population proportion divided by the square root of p1 minus p over n. This will be important later when we use this more often. We'll be using the distribution of a sample proportion quite often, actually, and it'll come up in surprising ways. And so this is approximately 2.57. So in other words, we're actually looking for the probability that our z random variable, the standard normal distribution, is less than or equal to 2.57. So we can find that using our normal area curve. So use a table if you want. You can use a calculator. But roughly, this is 0.9949. So it's almost certain that we would find a sample proportion less than or equal to the one in this sample. And in fact, if we had just looked at a sketch of the sample distribution, the sampling distribution, so here's my sketch of the bell curve, because it is a bell curve. So here's our mean, P, one standard deviation out, on the right, and one standard deviation out on the left. And if we simplify these values, actually, then we'll find the mean is 0.30, and then we add 0.065, and we subtract 0.065. And in fact, these are not that much far, that they're not very far away from this mean, right? So 0.235. So in other words, this defines this value, this defines this value, and that's the range that is one standard deviation away from the mean. And our 2.57 then, yeah, so 0.467 is all the way out here. So we were looking at computing the area of all of this. So it makes sense that we got 0.99, whatever. All right.